So now let's perform a correlation on a single image block. Later in the video, we'll discuss correlations involving multiple image blocks. So select the image series you want to evaluate and then click this icon to create a new evaluation. First, select the calibration file you want to use. By default, the software will automatically choose the default calibration. However, as mentioned previously, I personally prefer to manually browse and select the exact calibration file that I named myself and that I know applies to the image series being evaluated. So then click Next until you reach this screen. The options shown here can be useful in certain situations. Here you can browse and select a previously completed evaluation and then choose which settings or parameters you would like to import from that evaluation into this new evaluation. This can save significant setup time and help maintain consistency between evaluations. For example, the evaluation settings, the masks, the coordinate systems, and other setup information that we're about to go over here, these setups that are contained in previous correlations can all be imported into this new evaluation. Okay, so now click Finish. This begins the correlation. And now first go to the Input Data Selection tab. This is where images can be added or removed from the evaluation. This is also where additional image blocks can later be added to this same evaluation when performing multi-block correlations. Here you can also define the reference step and any desired rung steps. We're going to discuss rung steps later. For now, assume no rung steps are needed for this evaluation here. So in general, the reference image, the image that's defined to be the reference image, should be the first stable, high-quality image in the image series. This image serves as the reference image with respect to which all subsequent images are correlated. Now, but in some situations, the first few images may contain issues such as motion, obstructions, unstable lighting, whatever. But in such cases, the idea is it's generally best to just simply remove the undesirable starting images to where the first remaining clear image, which after removing images will be relabeled as step 0, this will become the reference image. So if images are added or removed and you don't see a reference step defined by this marker, then just right-click on the step and select that step as the reference step, and the marker will appear. So the additional details regarding adding or removing images, defining rung steps, reference steps, etc., organizing multiple image blocks into one correlation will be discussed later. Okay, now, but even if you're not defining rung steps and adding multiple blocks of images from different image acquisition series, in some cases, it also might be desirable. So you might, want to remove the first 5 or 6 starting images to get to the first clear image as the reference image. But it also might be desirable to remove images at the end of an image block. For example, this may be necessary if additional images were recorded after the fracture of the specimen. If you're recording images at 100 frames per second, and after fracture occurred, it took you a few seconds, maybe even 10 seconds to stop the DIC, stop the test, well, then you've got 1,000 images of just, you're imaging a fractured specimen. So what you want to do is you want to remove any unnecessary images at the back end of the image series. So all you need to do is just click on the first image to remove, hold Shift, then click on the last image. This will highlight all of the images that you want to remove at the back end, and then just select Remove Images. Okay, now next, click on the Mask Definition tab. The mask defines the region of interest where the DIC correlation will actually be performed. So you start off with your field of view, the entire field of view of the camera, the stereo camera pair. Then you define a region of interest within that field of view, because you're not going to capture images that contain the entire field of view. You only want to capture images within a specific region of the field of view. But now with the mask, you're telling the software, look, we're not going to correlate the entire region of interest. We're only going to do the DIC correlation on this specific region within the ROI. So in most cases, a single continuous masked region with one start point is sufficient. However, multiple separate masked regions can also be defined if desired, with each region is going to need to have its own corresponding start point. This could be desired if you have like physically disconnected regions, multiple crack tips, separate notches, etc. Now, when defining a mask near a specimen edge or a notch edge or a crack tip, crack boundary, or other kind of free boundary or special case region, the general idea when defining the mask here is to just extend the mask boundary up to the physical boundary of interest. Even though a DIC correlation will never be able to go all the way up to an edge, it's still useful to just define the mask boundaries this way, because what the software is going to do is just going to correlate as close to that boundary as it can. Correlation results cannot generally extend completely to an exact physical edge because each correlation facet requires a finite amount of speckle information surrounding the calculation point. Now, but smaller facet sizes and facet spacings and other parameters and tricks can often improve how closely the valid results approach an edge or a crack tip, provided sufficient speckle quality exists in the region. And later we're going to discuss how you can perform secondary localized correlations on the same image series using masks that are focused specifically around a notch or a crack tip or any other localized region of interest. So with this second localized correlation and this constrained mask area, you can use tricks, adjust the evaluation parameters, etc., to get a tighter correlation around that region. And then what you can do is that these localized correlation results can then be merged or appended onto the broader full field correlation results. We're going to talk about how to do all of this later in the video. But for now, here, we're just focusing only on a standard full field correlation of an entire specimen region, to where that region may contain edges, notches, or crack tips. In these cases, you still want to just extend the mask boundary up to the physical edges or boundaries of interest. So what the software is going to do is it's just going to correlate as close to these boundaries as it can. Okay, but now, where should start points be placed? The idea is with start points is that you want to choose a location where the correlation algorithm can confidently and uniquely track the deformation history at that location from image to image. So the question with where a start point should be placed is, where can the algorithm most reliably begin tracking the deformation field? The start point should be placed in a region with a high quality speckle pattern, strong contrast, and smooth continuous deformation behavior, so the correlation algorithm can reliably begin tracking the displacement field. So in general, you want to avoid placing the start point directly near free edges, crack tips, glare regions, shadows, or highly localized deformation zones where correlation quality may be reduced. For most applications, an interior region of the specimen with stable speckle texture and moderate deformation is ideal. Okay, so now once you have your mask and start point defined, or potentially multiple masks and multiple start points defined, go to the Evaluation Settings tab. Okay, now click this drop down here and select the Advanced Full User Defined option. If you're doing a non-specialized evaluation, meaning you aren't trying to optimize settings for correlation near a notch edge or a crack tip, or in a region where the speckle pattern quality is actively changing, like a necking region, then my suggestion for a general non-DIC expert is to just leave all of these parameters set to their default values, except for the facet size and facet spacing. So how do you select a facet size and spacing? Well, okay, come back to the ChatGPT chat that was started previously. And what I'll do here is I'll just tell ChatGPT that we created a new speckle pattern it's not too small. So I'll put 100, the speckle pattern is 175 microns on average, the speckle size, right? But in practice, you would have created a new speckle pattern with a slightly larger pore size mesh to get a slightly larger speckle size, because the ChatGPT told us that the speckle size was a bit smaller than optimum, which you don't want to be on the too small end of speckle size relative to the optimum size. Okay, so with a 175 micron speckle size speckle pattern, we want to ask ChatGPT that, so based on the information it has the field of view dimensions, the image resolution, the image sensor information, it has the speckle size. ChatGPT can recommend an appropriate range of facet sizes to use for the evaluation. And so for general full field evaluations away from crack tips or notch edges, larger facet sizes are typically preferred because they improve correlation robustness and the strain precision. And so the general idea is that the facet size selected will be several times larger than the average speckle diameter. And then the facet spacing to use is, you can set it equal to approximately 1/4 of the facet size. Here, since we told the software that we're doing a non-specialized general full field evaluation, the software knows that, okay, in that case, we want to use a facet size that's on the larger end. So I'll go ahead and go with the size it recommends, 35 pixels. And then here, so 9 times 4 is 36. I'll just go ahead and round the facet spacing down to 8 pixels. Okay, now with the evaluation parameters set, next click the Start Points tab. The purpose of the Start Point search is to establish the initial displacement correspondence between the reference image and deformed image, so the correlation algorithm can begin reliably tracking the displacement field. So if you defined multiple regions with multiple start points in the mask definition, you should see all of the start points shown here. But in this case, there was only a single region with single start point was defined, so that there's only a single start point shown here. So now click Start to begin the start point search. So each step is going to have a reported 3D residuum value. The 3D residuum is a numerical measure of how well the software is matching the speckle pattern between the reference and deformed images during the correlation process. In general, lower 3D residuum values indicate better correlation quality and greater confidence in the resulting displacement and strain measurements. For many well-prepared laboratory stereo DIC systems, 3D residuum values below approximately 0.1 are generally considered very good. Values of around 0.1 to 0.3 are often acceptable, and anything larger may indicate potential issues with the correlation. So sudden spikes or unusually large residuum values can result from poor speckle quality, glare, loss of focus, excessive deformation, poor lighting, or difficult correlation regions near edges or crack tips. So in the evaluation settings, this setting here is placing an upper limit on the 3D residuum. The correlation on a given step will fail if the 3D residuum at that step is found to be above 0.4. Now, this accuracy value here refers to the estimated uncertainty or precision of the displacement matching process. So how precisely can the software determine the subpixel displacement of the subset? The residuum value here, so not 3D residuum, just residuum, refers to the grayscale intensity mismatch between subsets. So how similar are the grayscale patterns before and after deformation? The software compares the speckle subset in the reference image against the deformed image subset, and if the grayscale intensity mismatch becomes too large, the correlation quality deteriorates. So large grayscale residuum can result from lighting changes, glare, blur, defocus, speckle degradation, saturation, shadows, or severe deformation. So this is more of an image texture matching metric. The 3D residuum is different, though. The 3D residuum is fundamentally a stereo reconstruction consistency metric. So conceptually, how well do the left and right camera solutions agree geometrically? It measures stereo reprojection mismatch error in pixel space. So large 3D residuum values can indicate stereo mismatch, poor calibration, out of plane issues, difficult correlation, or degraded subset matching. But again, since the correlation we're doing here is not a specialized correlation, we left all of the settings here as default, other than the facet size and spacing. Okay, so once the start point search is complete, next come to the Control tab and click Start to run the correlation. Okay, so now the correlation is complete. Click Visualization Settings to view the results. Set the graphical display to whatever parameter you want. This is purely graphical. What parameter is being displayed graphically here has nothing to do with the type of value you can view or export. This is just purely a graphical display. So like what you can probe or export from this field has nothing to do with what you're graphically visualizing here. This is pure visualization. Now, if you don't want to look at a two-camera view, just click here, then Control-click on one of the camera views. Okay, now here you can choose what image or step you want to view. But now you can notice, though, as you get further into the test, the correlation starts to break down a little bit. As you go further, it starts to break down a lot. And this is because of the degradation of the speckle pattern due to local necking, local plastic deformation. You're way past yielding around the notch here, so the speckle pattern is degrading. And we'll talk about later how this can be dealt with, to where you can prolong some of the correlation here. Okay, now you can also change the reference step if you want. So now here, this strain field is based on the image 3,148, but correlated relative to image 172. So if you, for example, here, this is just the accumulated von Mises strain going from step 1,109 to step 1,964. Okay, now the first thing we want to do is set the coordinate system. So click the Coordinates tab here, and then choose the Sensor System option here. It defaults to the Initial System option, and this is the initial system is the coordinate system that is established during calibration. During the calibration process, the very first calibration image that's taken sets the coordinate system based on the orientation of the calibration plate in that image. The camera coordinate systems are tied individually to each stereo camera geometry, each stereo camera sensor. And then the sensor system, you could think about it as being associated with an effective combination of the two stereo camera sensors. The sensor system is more of a unified stereo reconstruction coordinate system produced from the combined stereo pair. So click Create New. Now choose the Set Origin in X Direction option and press OK. Okay, so we first want to understand these options for the Z-axis orientation, these three options. So the Z-axis orientation, what they're saying is that no matter how we define the coordinate system, this is going to be a Cartesian coordinate system, an XYZ Cartesian coordinate system. So three straight axes that are all perpendicular. And this is how the Z-axis is defined, with one of these three options. And so you can see here that once we created this new coordinate system definition, 2 points showed up in the DIC field. And so with these first two options, we're going to have 2 points, a red and a turquoise point. With this third option, we're going to have a third point, a blue point. Okay, and so these points, any of these points can be dragged and put into a new location by just control-clicking and dragging the point. And then if you want to apply the changes you've made to the coordinate system, you click Apply here. And so we didn't see much of a change in the field because this is just like an equivalent von Mises field, which is like non-directional. But if we look at, let's see, strain in the X direction, let's say. So if I move, now you see the field change. You see, and so again, this blue point is only present for this third option. Okay, so now for any of these three options, the red and the turquoise point have the same meaning in that the red point defines the origin of the coordinate system, and the turquoise point is going to define the positive direction of the x-axis. Again, for any of the, even this third option, for any of these options, the red and the turquoise point have the same function. Okay, now what you want to remember here, and this is what confused me at first when trying to understand defining these coordinate systems, is that so the locations of these points, if you drag any of these points to a certain location and click apply, these points are not just like in the plane of the computer. The idea is wherever you place a point and apply that point is tied to the physical correlated coordinates of the field it's on top of. So you can't, I can't put this here and click apply because there's no correlation here. There's no, each of these points in the field, it has a displacement, has a strain. It also has a X, Y, and Z coordinate, right? So each of these points, wherever they're located, are tied to the X, Y, Z coordinates of that location. And we know that this is three-dimensional. This isn't just planar coordinates here. So this red point, the origin, has an X, Y, and a Z coordinate into or out of the page. Same here and same here. So even though this is a nominally planar specimen, there's still at a small level coordinates into or out of the plane of the screen, right? And I mean, if this was like a cylindrical specimen and you put the, you have the turquoise point here and the origin here, well, then the turquoise point would have a Z coordinate that's kind of wrapping around the side of the specimen. So these points are located in 3D based on the coordinates of whatever the correlation of the field is that they're sitting on top of. So keep that in mind. And so, okay, what are these different options for the orientation of the Z-axis? And which options are most optimum for this test here? Well, this is a nominally planar test, so that's obviously going to dictate how we define the coordinate system. So, okay, the first option, normal direction at origin, what does this mean? Well, you could think about this option as, so wherever you place the origin, so we place it here, the DIC system is going to look at a little group of points, a cluster of points that the origin is sitting on top of to estimate the local surface geometry and calculate a best fit surface or plane, and then determine a normal to that surface or plane. And that's the Z-axis, to where the positive Z-axis is then based on going outward away from the surface. And so what you can think about then is that when it comes to now the function of the turquoise point, all of the full 3D coordinates of the turquoise point aren't going to come into play for the x-axis definition, because the z-axis definition is fixed, strictly based on the origin point. Because again, the coordinate system is going to be Cartesian. And so what that means is that the x and y axes are going to have to lie in the plane that was determined based on the points that the origin is sitting on top of, that the z-axis is normal to. Because the coordinate system is Cartesian, the x and y axes are going to have to be in that plane. And so the idea is wherever the turquoise point is placed, it's strictly just defining the positive x-axis direction within that plane. And then the y-axis is just perpendicular to the x-axis in the plane, in that plane, with the positive direction of the y-axis based on the right-hand rule between positive x and positive z. Okay, and so now do we want to use this option for this specimen, for this test? Well, we could, but there's a better option. So let's look at the normal of best fit plane option. With this option, you can think about this like the system is going to take the correlation locations of all points in the entire field and then take the best fit plane of those points to be the XY plane, and then define the Z-axis to be normal to this plane with positive Z going away from the specimen surface. And so that's exactly what we're wanting to do here, right? The Z-axis is just going to go through wherever we place the origin. Let's just put it here. And then positive X is defined by the location of the turquoise point. Positive Y, again, is just based on the right-hand rule. Now, okay, how do we want to orient the X-axis? Where do we want to put the turquoise point? Well, what we can do is we can set this up to have positive Y be along the long axis of the specimen, the load axis parallel to the long axis of the specimen. Now, ideally, when setting up the test, we're trying to position the cameras in the specimen so that the long axis here, the load axis, would be parallel to the vertical of the camera sensor, but it's just, in practice, it's hard to get this exactly right. So what we can do is just use image J. So if we take a screenshot here, then we can see how much this is off of the vertical, by what angle. So about 0.44 degrees off of the vertical. And so then we just come here and orient this 0.443 degrees off the horizontal. A little bit more. There we go, close enough. Okay, now what about this third option? We're done here, that this is the ideal coordinate system for this specimen, but what about this third option? So now we get this extra blue point. Well, okay, so again, remember, wherever you place the markers, each marker is tied to the full 3D coordinates of the point it's on top of. And so with this third option, the idea is the software is going to calculate a best fit plane through the three non-collinear points. And then the Z-axis is normal to that plane away from the specimen surface. That's it. So this actually would work pretty well for our application here. If we just left it as it is here, and because it's going to calculate a best fit plane through these 3 points, right? So that's going to be pretty in line with the front face of the specimen, the nominal flat plane of the specimen's surface. But we would rather just do an entire best fit plane using all of the points of the correlation than just 3 points. This could be useful for another application with like a cylindrical specimen, right? Or if you've just got 3 separate unique points located in space and you want to do a best fit plane through those points. Okay, we'll go back here and there we go. Okay, so now what does this setting mean? This coordinates from setting. There's 2 different options. You have a static option and a dynamic option. Well, in the ISTRA user's manual, it says that the static option is where the coordinate system is defined at the active step and is fixed in space for all other steps, even if the object is moving. The dynamic setting is where the coordinate system sticks to the object and moves with the object. So to me, what this is saying is that for the static setting, whatever step we're on, let's say we're on step 1 or step 0, if we apply the static setting, then the origin will not move from this position in space, this position on like the camera sensor or the effective camera sensor location between the two cameras, no matter what the step. So the specimen in the background might move, but the origin is not going to move from this location in space. But if you go to other steps, the origin definitely does move. And if you change the setting to dynamic, what I found is that you seem to get the exact same behavior as you did for the static case. So what I've done is just default to leaving this set to static. And so at least from a visual standpoint, what the software is showing visually is that it seems as though, again, both the static and dynamic settings behave the same way, with that behavior being what is described here in the manual for the dynamic setting. Meaning, so it doesn't matter what step you define and apply the location of the origin. Once the location of the origin is defined, the origin has a location relative to distinctive features in the displacement and strain field. So like, for example, you've got this distinctive circular hole in the center of the field, right? And you could say that well, let's actually come back to step 1. You could say that, or step 0, you could say that the origin, the center of the origin is located 0.5 or 1 millimeter, whatever this exact measurement is, below the bottom edge of this circular hole along the center vertical axis of the sensor or the effective sensor plane between the two cameras. And so the idea is what the software is going to do is for each step, it's going to try and maintain this distance of the origin from this feature, right? Even at this step, it's that same distance from the bottom edge of this center circular hole. And it's the same idea as far as the location of the origin relative to any other distinctive features of the system. Okay, so again, I've just defaulted to always leaving this set to static. Okay, next, let's look at smoothing. When do you want to use smoothing? Smoothing increases precision, but you only want to use smoothing when it's acceptable. So how do you know if smoothing is acceptable? Well, the general rule of thumb you want to use is that for just like general full field data, just not a special case, for general full field data, so we're not talking about a special case near a notch or at a crack tip, if you're going to apply smoothing, so contour smoothing isn't applicable. This is more of just like for graphical purposes, in particular for with 3D graphs. So if you're going to apply smoothing, it's going to be displacement smoothing, local regression, with a kernel size of either 3x3 or 5x5, no bigger. You're either going to have no smoothing or local regression, displacement smoothing with one of these two kernel sizes. And so the idea is what you want to look for is you don't want to apply smoothing or a higher kernel size if you have too much clipping of maximum. So we can see here the maximum is 110. Then when we go to 3x3, it stays at 110. And at 5x5, it stays at 110. So that's a good sign. Now we can also check if we put gauge objects, we could put a gauge line going horizontal here. another gauge line spanning the entire section that's vertical, and then a circle here, let's say. Okay, so what we can do is we can put spatial plots. Let's put the von Mises strain spatial plot for, this is the horizontal line first. And when you apply smoothing, you're just looking to see. So we verified that maxes aren't clipped, maxes or mins, any kind of high magnitude values. Okay, but we also don't want to see the shape of contours like this changing as smoothing is applied. So that looks fine. Right? It's just smoothing out the noise, the kind of the rockiness, you could say. That's it. Okay, so what about the vertical line? All right, so no smoothing. It's just making the, it's not changing the overall shape of the line. It's just smoothing out the line. That's perfect. Okay, let's check the circle. Turn this off. So that looks great, at least for the von Mises strain parameter. But you also want to do this same inspection for other parameters. Do this inspection for displacement in the X and Y directions, the normal strains in the X and Y directions, as well as the shear strain field in the XY direction. If all of these parameters pass, then you can apply the displacement filter with whatever the kernel size. Okay, so that's it. Now you have your data. You have your coordinate system set up. You've applied any smoothing if applicable. So now that's it. You could do whatever you want with this data. So you could probe certain points. Here at this point, you can look at its coordinates, displacement values. This is RBMR, is rigid body motion removed. And you've got the different strain values. So the strain in the Y direction here, let's say. So yeah, so this is von Mises strain, right? But this is just graphical. It doesn't matter. You can export any values you want. It doesn't matter what you have shown in the display. So here's the engineering strain in the Y direction. Let me do engineering or true strain in the Y direction. So add report entry. So there you go. There's the true strain in the Y direction at this point, the Y direction being the load direction, the long axis direction at this point, and here's the precision. And this is in millistrain. Okay, you could do a line. So you just left click, and then to close out a point or an object or a shape like a line or a polygon, the final point you add, you want to right click, and that closes it out. That'll add the line, finish it and add the line. So here, what's the length of the line? The length change. You've got line strain, line engineering strain, line true strain. It's like a virtual strain gauge, right? So the true strain on this line, and there you go. You're going to get higher precisions with these averaged strains, averaged across the line. You're going to get higher precisions than like point-wise values. Or you could, do a polygon, right-click the last point to close out the polygon. So you can, there's just contour values. You have the average strain within the region, the average strain along the edge, the max strain along the edge, whatever you want. Okay, now there's also the signals that are coming in from the hydraulic unit. The load signal, usually you'll always have the load signal, but depending on your application, you might choose to also have an extensometer signal. These are the analog channels going into the trigger box. So here's the load, and here's the strain signal. And this absolute and relative, what that's referring to is absolute is just the absolute load signal, just exactly what the value is. Relative is just subtracting out the load at the reference step is all. So here you've got 13.35, here you've got 12.519. So 13.35 minus 12.519, 0.831. So if we come to the reference step, you can see all these values update. This should be 0.831. There you go. And relative 0. Okay, so now let's see. As far as the color scale, the display of the color scale, I don't think there's a way to tell the software that, okay, I don't want to include any colors from here up and here down, or like I only want to include blue. You have to, as far as at least in the Istra software, you have to use the full rainbow. And we'll talk about later in the video, there's a workaround, you know, if you, in terms of dealing with certain graphics, you could use MATLAB to whenever you're appending data together. So we do refined correlations to where you can do a separate correlation that will fill out a lot of this and even get close to the notch, and you could append all that data together, but you can't look at the final graphical result. There's no way to kind of add that together and put that into one final correlation in Istra, but you can do that in MATLAB, and we're going to talk about that later in the video. And so even in MATLAB, you could you could clip off the color scale too. MATLAB or Python, you could have the color scale not be the full rainbow. So you can't, I don't believe there's any way to do that here in Istra, but what you can do to work with to adjust the scale is, so right now it's an automatic scale at each step. It just, what's the max value, what's the min value, the max is assigned, you know, the dark red, the min's assigned like a purple, and then every shade in between goes in between. It does that for every single step. It automatically updates the full scale based on the rainbow. Now, if you don't want an automatic scale, you can uncheck this and set your upper and lower limits, and this is universal for every single step. So you can see how that works. And so now, but what values would you want to potentially set as the upper limit and the lower limit here, this universal upper and lower limit? Well, maybe you want the absolute maximum value throughout every single step and the absolute minimum value throughout every single step, right? Well, that's the purpose here. You say calculate, and there's a lot of steps here, so it's going to take a few minutes, but it's going to calculate the absolute max and the absolute min value for this visualization throughout all steps. And then you can just click take as limits and it'll put those here. Or what you can do is, let's say you don't want to do this because there might be outliers. These like one-off max really high values and one-off really low values. Well, this is the P98 and P92. This is the 98th percentile value, and this is the second percentile value. So you can take those as your limits and put that here. So that's useful. But again, you're still having to always use the full rainbow, which what I found can be problematic in certain circumstances, especially like simple tension tests with just uniform non-notched fields. Okay. Now you can come to like this gauge point here, and you can choose whatever value you want. So the true effective von Mises strain at this point, you could right click and say export to ASCII. You choose your file name and location. You could you could export the value at the current step. You could export this value at all steps, or just steps from, specific, whatever specific steps you want. And it will output the von Mises strain value with the uncertainty at each step that you choose. And same idea with, any of the parameters with the line, the polygon, etc. Now, but what if you want, in most cases, we're going to want the entire field of data at every single point. Well, if you come here to File, Export Data, you'll choose just the ASCII here. Okay, so you could just export all steps, or you could export the current step that you're at and choose what reference step you want. So that's like you're setting the reference step here. But if you choose all or the steps here, then it's just going to assume that it's going to make the reference step be step 0 by default. So you could just do like step 4000 to step 4964, for example. Choose your file name and the location. And so if we just do the current step, let's just do the current step. And okay, so this is just a text file. And so if we open this text file in Excel, there we go. So we've got, at this step, you've got these array of points, like 8,500 points, and here's the coordinates of those points, the x, y, and z coordinates, and here's the array of different values, all of these different values with the corresponding uncertainties, as well as the analog and the analog signals, the load signal and the extensometer signal, as well as there's the timestamp. So the test started at time t is equal to 0. Step 0 is at time 0, and this is when the trigger box is saying that this image was acquired, this pair of images. All right, 15.8499. And so you can see if we plot this here, there you go. So these are just little individual points throughout the entire field. That's the XY coordinates, right? I stretched it out a little bit. It's more of, should look more like that realistically. Now, if you don't want to export all of these values, then I believe there's a way to, so you come to settings here, and I believe if you, let's say you unchecked all of these. Okay. So let me close this. And okay, well, it's already. Okay. That's fine. Now, you could reopen that correlation here. And so all those plots, it's a limited number of plots now. It's not that vast array. So I believe now if we exported, let's do that same step 634. then okay, so yeah, so now you don't have to export every single data point, every single Lagrangian, engineering, and true strain. You know, it will take less time when you're exporting thousands of files. It can take a while to export, and so it's nice to be able to eliminate some of those values if you need. Okay, so now we're going to talk about special cases. The first special case is performing stereo DIC on a non-planar specimen. So here is a cylindrical dog bone specimen, for example. Thankfully, there's actually not much difference at all regarding everything we've discussed in this video as far as, you know, if you're dealing with a planar or non-planar specimen. The calibration process is the same. The calibration parameters, masks, start points, rung steps, smoothing procedures, and evaluation strategies are all fundamentally approached the same way. The focusing process is also very similar, although there is one important difference that we'll talk about in a moment. So, in my experience, there's really only two practical differences when performing stereo DIC on planar versus non planar specimens. The first difference is that lighting becomes more important and generally more difficult to optimize with non-planar geometries. For example, just look at the glare and reflections here on this cylindrical specimen. So with non-planar geometries, reflections, glare, shadows, the shadows resulting from the different viewing angles, right, across the surface all become more significant and more pronounced. So how do we address this? Well, polarization filters are extremely effective for reducing glare and reflections. That's one of the primary purposes of polarization filters. So if you plan on using the 50 millimeter lenses for non-planar stereo DIC, you'll likely want to purchase a set of circular polarization filters for those lenses, just like we currently have for the 35 millimeter lenses. And as we discussed earlier, if even with using a circular polarization filter, glare and reflections are still present. So like overall, they're really severe. Then we also have the polarization sheets that you can add directly to the lights. But then furthermore, this is where using the flattest paints possible becomes important. Okay, now the second major difference between planar and non-planar stereo DIC is that depth of field becomes much more important. So the reason the aperture is stopped down, was closed to f8 for the testing, is because closing the aperture, the more the aperture is closed, then the more the depth of field is increased. The depth of field being the total distance in front of and behind the optimum focus distance over which objects remain in acceptable focus. So with DIC, we're thinking about the speckle pattern. So the depth of field being the distance from the optimum focus distance in front of and behind the optimum focus distance for which the speckle pattern remains in acceptable focus for correlation. And so for planar specimens, this is usually not something you have to think about very much because nearly the entire specimen surface is going to be well within the depth of field. But with non-planar specimens, different portions of the surface are located at different distances from the cameras, right? So therefore, the depth of field in the non-planar test case affects how much of the speckle pattern across the object can be accurately correlated. Now, what you want to think about, though, is that this is generally not going to be like a hard cutoff point where you get to some specific distance from the optimum focus distance and correlation just suddenly stops. This hard depth of field boundary. No, instead, it's more like as you get further away from the optimum focus distance, the focus is going to gradually degrade, and along with this, the quality and precision of the DIC correlation will degrade. until eventually you get to a point where the focus is too poor to where the DIC can't correlate. The speckle pattern is too blurred. Now, okay, so earlier I mentioned that the focusing process is slightly different for planar versus non-planar specimens. So remember that the focusing process was when we fully opened the aperture and then we're dialing in the maximizing the global sharpness parameter. So this process, when it comes to a non-planar specimen, can be different because, okay, for these cylindrical specimens here, if you went through the focusing process using a cylindrical specimen itself, then what you'll be doing is you'll be focusing directly on the visible front surface of the cylinder. So like you can think about the tangent plane to the front face of the cylinder. So then the optimum focus distance in that case is biased towards the front tangent plane of the specimen. And that might not be what you want, right? You might want the optimum focus distance to be a plane that's going through the central axis of the dog bone. And so one way to accomplish this is you would first perform the focusing process using a flat specimen or a flat target located at approximately the center depth of the eventual cylindrical specimen geometry, and then afterward install the cylindrical specimens into the grips. However, you can think about, though, that this ultimately depends on the specific application and the depth of field capabilities of the optical setup. For example, just like hypothetically, if you had a cylindrical specimen that had a really large diameter, well, then if you had the optimum focus distance being going through the central axis of the specimen, well, then the entire surface of the specimen, the entire front surface of the specimen would be out of focus. So maybe in a case like that, you do want to just go ahead and do the focusing process directly on that front face, that visible front surface. So ultimately, you'll just need to evaluate your specific application, the specimen geometry, and the depth of field capabilities of your camera lens configuration. Okay, so now what if you want to have two or more separate blocks of images in the same correlation? Meaning, so here are DIC images collected during a fatigue test that was conducted on this center-notched tensile specimen. The load rate was 5 hertz, and the frame rate of the DIC system was 100 hertz. So we ran the test from start up to approximately 12,000 cycles, 12,000 load cycles. So if the image acquisition had been running continuously from test start to finish, then at 5 cycles per second, 12,000 cycles, 100 frames per second, that would have been about 6 million images the DIC system would have needed to collect in a single recording session. Well, our system can't do that. So instead, what we did was we collected images in 3 blocks of image acquisition, about 2 minutes of image acquisition, so about 12,000 images. The first image acquisition block started at the start of the test, so at cycle 0. The next 12,000 images we started collecting at as close to the start of the 5,000th cycle as we could, and then the third block at the 10,000th cycle, the start of the 10,000th cycle. And the idea was that, so, the test started, we started collecting images. 2 minutes later, the images are acquired. So now we offload the images, and during that time, you can't do anything with ISTRA, but then those images get offloaded, and the ring buffer is reset then and restarted at cycle 5,000. Those images get offloaded, you reset the ring buffer and start it again at cycle 10,000. Okay, so now the question becomes, how do we process all of these images together as a single DIC correlation? Well, initially you might think, why not just run a separate correlation for each image block? Well, the issue with that is that, so for the second and third blocks, the images would be correlating back to just the initial images of those respective blocks rather than back to the initial image of the first block, which is what we really want. But then furthermore, it's much cleaner and less time consuming if the entire fatigue test can exist within one organized correlation, right? And so, yeah, thankfully we can do that. So what we do is, here is, all right, you've got for this, we ran 4 of these tests, but let's look at at test 4. So with test 4, you've got 3 separate image blocks of about 12,000 images, right? 11,999. You have these 3 separate blocks of images. This was started at cycle 0, this at cycle 5,000, this at cycle 10,000. So we're going to select the first block and start an evaluation. Just call this DIC training. Okay. And then again, I don't like to leave this as the default because you've got so many tests mixed in everywhere. I like to just name a calibration file that's similar to the image series name. So this was on 5/14/26, and I know it's this one, but I mean, I could have named it even better. I had to do some updated calibration. So it's this correlation or that calibration. Okay, now I'm not going to pull in any parameters just to walk you through this. Okay, so now let's come to the input data selection tab. And the first image as the reference step is fine. We don't need to delete any kind of bad images, like the first 10 images or something. So this would be the reference step. And again, you could right click and you could make any step. We could turn this into a normal step. So it's just like the empty circle. We could turn it into a rung step, or it's already a reference step. We could make it, a reference step or the reference step. So you could see, I'm probably going to mess this up. Yeah, there's only one reference step. So, but you can set multiple rung steps. Okay, and so now in general, if this was just my project, we're leaving all of these images and we just want to add the images from block 3. Just append the images from block 3 here, and then, or block 2 here, and then next block 3. And then just go from there. It's going to be a large correlation. It'll take a few hours to run the evaluation, but that's fine. Okay, but for the purposes of this video where I'm trying to just be able to do this quickly, and this actually is a good illustration if this was your test and you were wanting to try out some evaluation parameters and different settings and masks and see how the correlation comes out, and you don't want to run an entire full correlation every time you want to test out some settings until you're going to find your final settings and then run the full correlation. This is something that you would do. So yeah, this is actually perfect. I can show you this. So we want to create like a condensed image set here so we can run some test parameters. We could do some quick correlations to see what's the optimum facet size, facet spacing, the mask definition, etc. So what we're going to do is we're going to take 500 images from each block. So we're at step 0, so let's go to step 499. And now we want to delete every image past the 500th image. So from step 500, shift, click, remove steps. And just note, you want to it's going to, every time you have a new set of images, if you remove steps, add steps, it's going to renumber them. So just be aware of that. So now we've got, nothing's really changed here. We're still just step 0 to step 499. But okay, so if this is the step, then what is this? Why are they kind of saying the step twice? Because this is series. So this is the overall step number for this entire evaluation. This is the step number for the image acquisition series. So right now we only have one series, but if we come to add steps, and we're going to say, so these were the steps that were, so here we've highlighted this image acquisition series, this block of images. These are all the steps that we just deleted, so we can add them back if we wanted to. And now just to show you here, it's saying, so if I want to append, I click here, I want to append just this one step. I could control click, I could select them all, but I just select step 507 here from this image series. Okay, so let me show you. Well, okay, actually, I said that wrong. So no, this, if we click append here, we're going to be appending other image series up here. So we've got, we want to append for that test for the second block of images. And now if we clicked here and appended another series, it would call that series series 1 and change this to series 2, I believe. So we want to leave, I mean, we could rename this whatever we want, I believe. Or no, we can't. So if we select here and then now we append, it'll make the third block series 2. So test 4, we have these 4 blocks of images, 12,000 images. Okay, so the idea is you've got none of these images within the selected image series are currently included in this evaluation. So if we come back to series 0, the block 1, these are all the images we deleted. So if we select an image or a group of images, it's saying, okay, 7 steps will be added at position 2. This one step will be added at position 2. What are they talking about here? They're talking about, so that's what we have, that's what we selected over here. So if I clicked OK, it's going to add step 255 from series 0 after step 2 here. So let's do that and see what happens. So it renumbered everything on the left, which is kind of confusing, but we still retain the original information on the right. The third image is from the series 0, block 1. It's the 200 or the 2055th step. So obviously we don't want this. So we'll remove, and now it goes back to where it was. But you see where images get inserted depends on what you have selected when you come to add steps. So what we want to do is we're going to click here and click to the bottom. So now when we click add steps, whatever steps we select are going to be added, appended on after this step. So what we want to do is we're going to come to the block 2 series, that they're calling it series 1, block 2, and we want to add on the first 500 images. So shift click. So 500 steps will be added. Oh, no. Okay, that we're fine. Series 0, step 1, step 2, step 3. And then we get to 499, the 500th image. And now it changes to series 1. So yeah, that's right. So now we come here, click add steps. And we're going to add the first 500 images of series 2 or block 3. And there we go. So now, but on the left is like the official step number for this correlation. This goes from step 0 to step 1,499. So that's 1,500 total steps. Now, let's see. You might be wondering, well, don't we need to, so you can even have tie a certain calibration file to a given step. So don't we need to change the calibration file associated with like the different series? Well, no, because this was all the same calibration. We calibrated the system and we ran this test. We didn't change the calibration, right? This was all the same test. So they're all associated with the projection file 0. That's the file name that I chose when starting this evaluation. I could change it here if I want to. Or we can add a second one. Okay, but now, we're not done yet, though. We're not done with these input steps yet because we still want to add rung steps, label certain steps as rung steps. We don't have to do this. We can absolutely run the correlation without doing this, and it might turn out okay. But if you understand what rung steps are and how they're used, then you do want to go ahead and add rung steps here. So let's talk about rung steps. What are rung steps and how are they used? How do you use them? So first of all, again, remember that within a general DIC image series, you're going to have one main reference step. And in most practical cases, that's just going to be the first image in the image series, step 0. Now, yes, you could acquire a series of images and maybe the first like 50 images, there's something obstructing the view or whatnot. And the quality images for DIC didn't start until the 50th image, let's say. Well, then in that case, what you're going to do is you're going to delete the first 50 images, the first 49 images, and make the very first step the reference step, and it's just going to renumber that's going to be the initial image step 0 anyway. So that the general idea is that the first step 0 for a DIC image series, in general, that's the reference step, and there's only one reference step. There's always a single reference step. So conceptually, the idea is that there's this one primary reference image for the correlation, the reference step, and all subsequent images are fundamentally related back to that reference image. Okay, so it doesn't matter how many images were collected in the image series, how long and drawn out the image series is. Maybe images were collected over days. If your test setup is such that you're performing a DIC correlation on this single image series and you have this main reference step, the first image, then even if you have days worth of images, millions of images, the fundamental idea is that conceptually, every single image after the reference image is being related back to that reference image. It's being correlated to that reference image. And so like from a very basic standpoint, the way you can think about this is the DIC algorithm is just taking every single image. Let's say there's no rung steps defined. Let's say that you have some, 6 million, 10 million images collected over a week, and all of this entire image series is one DIC evaluation that's in reference to the first image, the reference image. Then what the DIC algorithm is going to do is it's going to take every single image from first to last, and it's going to take the active image that it's at a certain step. It's going to take the image from that step, put the reference image next to that step, and then do its image matching process, the DIC process, and perform the correlation. Every single step is going to be compared to the reference image, assuming there's no rung steps defined anywhere. Okay, so the idea is what rung steps are used for is if you ever get to a point where there's become a significant deviation from the way the specimen and the speckle pattern looks from the reference image due to anything, significant amounts of deformation or rigid body motion or lighting changes, whatever, speckle pattern breakdown, whatever. If there's been a large amount of deviation from active images to the reference image, then rung steps are used to bridge the gap from the active image to the reference image. Because if there's too much of a difference in the image, that can degrade the performance of the DIC correlation. That's the purpose of rung steps. Now, what you want to think about, though, is to really understand the fundamentals of how rung steps are used, what they do, and this will be helpful for understanding how rung steps are applied to try and help with the correlations of speckle patterns in necking regions that we're going to talk about in a few minutes, is that so it's not like rung steps are only applicable if you're acquiring 1 million images. You're acquiring so many images, or it's images acquired over a week time span. No, it's strictly about the difference from one image to another under whatever the circumstance. From a fundamental DIC standpoint, where you'll always have theoretically always have a high quality speckle pattern from start to finish, the differences from large differences are going to come from large deformations and or rigid body motions. But from a practical standpoint, there could be differences in images, could come from lighting changes, speckle pattern breakdown, etc. And so that's the purpose of rung steps, that they're to aid the DIC algorithm when the specimen and the corresponding speckle pattern have deviated significantly for whatever reason from the reference step. Rung steps help the DIC algorithm as far as bridging that gap. Okay, so why not just add, 100 rung steps? Well, for every rung step, there's going to be a little bit of precision loss. So you don't want to just arbitrarily add rung steps. However, if a rung step is added at a position where it's needed, then the accuracy lost because of the gap bridging is made up for, and most likely and then some, by the accuracy that would have been lost if the DIC algorithm didn't have that bridge to work with. Okay, and so more generally, what a DIC algorithm is going to do when it's performing an evaluation on a single series relative to the first reference image, for every single active image, it's going to take that image and put it side by side with the next closest rung step image, perform the correlation, then go to the next rung step, and the next rung step all the way to the reference image. Okay, so let's say then you have a image series of 1,000 images, and you decide you want to add 3 rung steps to the image series. Where should the steps be placed? Well, the answer is it's not that it's necessarily to simply divide the image series evenly into fourths. So you're going to put a rung step at image 250 and 500 and 750. No, the optimum placement depends on the nature of the test. And if you think about it, the rule for optimum placement of rung steps is simple. All you're trying to do is, they can be placed anywhere. It depends on what the test is doing, right? And what the optimum placement is going to be, whatever placement minimizes. So as the algorithm goes through step by step, and the algorithm is, and from that simple perspective, putting the active image next to either the reference image or the next closest rung step image, for any given image matching process the algorithm does, you're trying to minimize the difference between any given 2 images. That's the whole goal. So whatever placement of rung steps minimizes that difference, that's the optimum placement. Again, the algorithm's going through one image at a time. It's taking the active image and putting next to the active image either the next closest rung step or the reference step. So you want to place rung steps with the goal of for any of those given image matching processes, for every step that the algorithm goes through, you want the minimum difference between any given 2 images that it has to correlate. Okay, so with that in mind, what should we consider doing here as far as rung steps? Because, okay, if we go to step, let's see. So we're going to see that, you can see that image change, right? It's not much, but you have that jump. And this is more than just jumping from one block to another, because we actually cut the block short. This should be going to step, all the way to 12,000. And then we go to the next block. We cut this short at the 500th step, but it doesn't actually really matter that much because it's just a fatigue test. It's not like this is a continuously, like a monotonic continuous deformation test. But still, okay, we have a change there. And then another change there. So what should we do? Should we just make, the first image of blocks 2 and blocks 3 would be rung steps? Well, yeah, that would probably work fine. And again, just looking at this, I don't think it would, the correlation would do too badly even with no rung steps. But just to kind of go through a thought exercise here, I think you would definitely want to make the first image of blocks 2 and blocks 3 to be rung steps, right? Because that's the whole idea of, if you were going to run just totally separate correlations on the image blocks, that's what those separate distinct correlations would be doing, just correlating every image back to the first image of the block. So let's go ahead and do that. Okay, but now do we want, so what's going to happen is when there is, when the algorithm is running a correlation on step 503, it's going to put these two side by side and do the correlation. Then you could sort of, in a hypothetical way, think about, we've got some new image, and the algorithm's going to take this new image and just put the reference image, go straight to the reference image. So it's going to jump over this. It's still going to be sort of, you could think about going from block 2 all the way to the reference image. So it would probably be a good idea. I mean, yes, there will be some precision loss, but I think it would be worth the loss to make this a rung step as well. Because what you'll be doing is, so yeah, you can think about this like, again, so if you had the 3 separate image blocks and you did a distinct correlation on each. So the entire correlation, every image is correlated with respect to the first image of the block. So what we're doing here now is we're taking those correlations, and when we jump to block 1, we want to jump to the kind of the start of block 1, not to the end of block 1. So we're going to make this a rung step. And I think this would really be necessary to do it this way if there was significant differences between the blocks. The images, there was really significant deviations in the images as far as deformations, etc. Here, this is probably, my guess is a little bit overkill, but I think it's illustrative, really helpful to understand how rung steps work. So let's put okay. So now we're set. Now we've got our image series and with reference and rung steps defined. So now let's go ahead and go to the mask. So right here, this is just another, we're doing another correlation. It's not a special correlation in terms of we're focusing on a crack tip or notch edges or regions that have like degraded speckle pattern. This is just a general full field correlation that where the field may or may not contain a notch, but we're not focusing on the notch or the crack explicitly. So the mask, then we still just put the mask borders right up to the notch edges, and the software is just going to correlate as close to the notch edges as it can. And then we'll come back afterwards and refine the correlation for the near the notch and the crack. We'll talk about that next. Okay. Now and this is all at the reference step. The mask is always going to be defined at the reference step. Okay. All right, let's just put start point there. Okay. Now with the evaluation settings, I'm going to leave them default and make the, off to the side. I had done the facet size analysis myself. That wasn't shown in this video. So let's put a 35 pixel facet size, 8 pixel spacing. And actually, what you can, another trick, I'm actually going to leave this at 17. So something else you can do is, what we're doing here is we're trying to run quick correlations so we can test out, I'm doing that for the sake of this video, but if you were, you would want speed to do this quickly because you're testing out facet sizes and mask definitions, etc., right? Especially when it comes to the notch refinement and crack tip refinement. You're wanting to do these quick correlations. That's why we condensed down the total images. Well, if you make the grid, the facet spacing too small, then that really slows down the correlation time. But it's okay to make this larger here for the sake of speed, because in general, if we don't make this too big, the only thing we're losing is just point density, the spatial resolution, by raising the grid spacing. We're not losing anything in terms of the quality of the correlation itself, the precision. So as long as you don't make this, you want to make this a little less than half of the facet size. So 17 times 2 is 34. That's fine. And again, the idea is once you dial in all of your settings, then you could come back and run the main correlation, put this down to a small size, and it'll go a lot slower, but you'll have a lot denser field, a lot higher spatial resolution. Okay. So now we only had a single start point. So we only see one start point here. We only put one start marker. And okay, let's Do the start point search. That's a good residuum. Check a few points. Yeah, that all looks good. Let's see how the residuum changes going from series 1 to series 2. So it jumps a little bit. That's fine. Remember, less than 0.1 is excellent. 0.1 to 0.3 is good. Greater than 0.4, it's set to, it won't even correlate. Actually, look, that one's less than 0.1. Let's see. Now we're in series 3, still have a good residuum. Okay. Now, okay. Let's see what we've got. What happens when it jumps from one series to the next? So we can see if smoothing is applicable here. I'll just check the von Mises strain plots. But the idea is, in general, you'd want to check the different parameters we talked about. So just put gauge line going here across the field. Okay, so I mean, actually, let's check the displacements. So displacement, just to show you. Well, okay, we have to do the coordinate system. Let's just, this will be close enough. This actually does look very close to a line with the actual vertical anyway. So normal best fit of plane. Okay. Yeah, I actually think this already might be very close to true vertical anyway. Okay, so let's see. X displacement, rigid body motion removed. Okay. I mean, that field looks pretty smooth to me. So a spatial plot. Okay, when you add smoothing, it just stays a line. That's fine. Then what about, let's just do the Y displacement here. Why not? Well, no, I don't want to change it because you would still check Y displacements for all of these elements. So, okay. The line just stays a line. And then the circle here. Yeah, it's just smoothing out that the shape of the curve doesn't change. So, okay, we'll leave local regression with this kernel size. But again, you'd want to technically go through this process for not just the X displacement, but other parameters. Okay, but now note that you see a, plot like this. This actually looks pretty good, but is this? Some of these plots have a noisy, kind of a noisy look. This isn't too bad, but like for like a simple tension test, for example, you'll see even at pretty, you know, not the strain levels, the load levels or the deformation levels aren't that low. It's prior to necking, but you're out of the elastic region and you're seeing a noisy looking strain graphic. I can show you what I mean here. Here we go. So step. So, okay, we're at, 4.6 to 2.4 millistrain. When you think about 2 millistrain is 0.2%. That's like a general yield point of a metal. But even at higher loads, if these magnitudes were at, 10 to 7 millistrain, 10 to 8 millistrain, if that was the range here, you would still see a noisy looking graphic like this. This looks incorrect, right? We know that strains, for a simple tension test, you're supposed to have a uniform strain field here. This should be close to a single color. The displacement field looks correct, even at low loads, right? But the strain field looks like something's wrong. Okay, remember that. So with the displacement field, the displacement field is not supposed to be a single value. The displacement, even at low strains, you're going to have a higher displacement near where the load is being applied. You have the bottom grip pulling down than you do up here. But the strain field, from an FEA standpoint, FEA would say that if this was, a nominal simple tension specimen, you have the exact same strain value everywhere here. This should be a single color, according to FEA. And it looks like it's the opposite of that, right? It looks noisy. So what's going on? Well, you have to be careful because it's just really more of a graphical issue. I could create a full field of data points, like a grid of data points, say 1,000 data points, and their nominal value is, let's say, 500, and I could make them infinitely precise. 500 plus or minus 10 to the minus 1,000, okay? But then using a color scale like this, like a full rainbow color scale where red is 50 or what was it, 500 plus 10 to the minus 1,000, and then purple is 500 minus 10 to the minus 1,000, you would still get a noisy looking graphic, even though the field is it's perfectly precise. It's infinitely precise. It's experimental data, so it has uncertainties, but every value is the same exact value with infinite precision. You'd still get a noisy looking field. So you have to be careful. Don't let these graphics, all we need to do here is just probe a point. If this test was run correctly, according to the way that the Dantec system is supposed to be used, all you need to do is just probe a point and see. Okay, so this point, von Mises strain, the precision is 0.2 millistrain. That's the general precision of the von Mises strains in this field, 0.2 millistrain. What does that mean? Well, 2 millistrain, that's 0.2% strain. That's the general yield point of metals. So 0.2 divided by 2, it's that percentage into the elastic region. So it's a pretty good precision. So yeah, I mean, that's the idea. You look at these fields and it's easy to get intimidated by some of these strain fields that they seem to look wrong. Something seems off. Be careful with these color graphics. What you really want to be doing is, okay, so how precise are these strains? This is true effective von Mises strain, but I can probe a few different regions here and just take a look and see. I can look at the precisions of any of these parameters. 0.2 millistrain, the principal strains, 0.2 millistrain, the displacements. What is that, 0.7 microns? That's 0.1. 0.19 millistrain, this is this point, I believe, yeah. So that gives you a sense for the precision of the values in this field. And everything seems to have gone fine as far as jumping from one block of loading to another. Okay, so, but now, what if we want to potentially, I mean, this isn't bad at all, but what if we wanted to try and close in on this notch a little closer, fill in some of these gaps? With DIC, you'll never, in general, be able to correlate up to an edge. That doesn't make sense from what exactly DIC physically does, but still, maybe we could get a little closer here. So when it comes to refining correlations near notch edges, near crack tips, or like we saw with the first correlation that we ran late in the correlation when necking is occurring in certain regions and the speckle pattern is breaking down. The general idea is the way you're going to do this is so there's not, at least as far as I'm aware, there's not a simple way of doing this with sort of a seamless all-in-one process using the ISTRA software. Meaning, so like we could perform another correlation, refining around the notch, and then easily just append all of those data points onto these data points, and we can look at a full graphic of the new updated data set. Unfortunately, there's no simple way to do that in the ISTRA software, but you can use AI to help you write a MATLAB or a Python code. And what the code is going to do is, so you would start by, after running this correlation, so you test out different settings, facet sizes for this is the full field. We're not doing any refinements, just the general full field. So you get the correlation you're comfortable with, the settings, and you run the full correlation for all images, and you export the full data sets for the full field into the big step files. So you're going to have a file of, this would be 12,000 steps for each block. It would be, so 36,000 total text files. With each text file has this full field of data. And if you ran it with a small grid spacing, then you'll have tens of thousands of data points on each step. So 36,000 total step files, text files, and within each file, you've got tens of thousands of data points with all of these parameters and their uncertainties. It's a lot. It takes a lot of process. Okay, but what we saw was that the first, or close to the first 3 columns, are the coordinates of each of these points, the X, Y, and Z coordinates. So the idea is, what you're going to do is you're going to export all of this data from just the general full field, nothing specialized. Then what we'll do now is we're going to run another correlation, a specialized correlation, either near a crack tip or here around a notch, or with the degrading speckle pattern, the refined correlation with the goal to correlate some of these extra points. And you're going to export the step files for the refined correlations. And then what the MATLAB code or the Python code is going to do is it's going to compare the files at each step from the specialized and non-specialized correlation and look for overlapping coordinates. And wherever there's overlapping coordinates, it's just going to delete the specialized data points for those coordinates. But wherever there's non-overlapping coordinates, it's going to append those to the main general correlation step files. And so when you're done, you'll have these new appended text files, 36,000 total text files with all of this appended data from this original correlation. Now, you can't just upload those back into ISTRA and get a new graphical plot, but you can use Python or MATLAB to create your own spatial plots. But the advantage there is you can apply whatever color scale you want. You can cut off red or just use a blue scale. You can still use a full rainbow scale. You can scale the graphic however you want, and you can easily make the MATLAB can make the output transparent, however transparent you want. So you could think about sort of taking this off and just overlaying the MATLAB plot. Now, but what's also nice about this is that once you've got all your data able to, like if this is like for a big project of yours, you've got all of your data kind of easily imported, set up to be imported into MATLAB. You can use MATLAB to do whatever you want with the data, to analyze it however you want. Okay, so let's start with, we're wanting to do a new correlation here, but this correlation is based on trying to refine around the notch. It's a specialized correlation near the notch. So we would most likely just start a brand new correlation so we don't lose this data, but I'll just reset this here. I don't need this data. Okay, so what's different if you're trying to refine a DIC correlation? This is really near an edge of interest. We don't care about the correlation near these edges, but these are edges that we care about. And with a crack tip, it's a similar idea, but the crack tip is a little bit different in that with a crack tip, you also have degrading, the speckle pattern is degrading at the crack tip. So it's a combination of speckle pattern degradation and you're trying to correlate near an edge. Here, the speckle pattern is remaining intact for the most part. So it's more about how do we get up as close to these edges as possible without losing too much precision. Well, okay, well, in this case, what's going to help is a smaller facet size. We can't make the facet size too small because then there won't be enough of speckle features within each facet to do a correlation, right? But the idea is the smaller the facet size, then the closer we can get up to the notch edge, right? That's the idea. Now, something else to keep in mind is that when it comes to the mask definition for a specialized case, you want to try and keep the masked region as confined as you can to what you're focusing in on. So we want to, what I'll do is we want to just take this mask and put it around the region we're focused on here. Leave room for a clear, distinct start point. Yeah, that should be fine. Okay, now we can still use a large facet spacing just for the sake of we're testing this out and seeing how it works. And then for the final correlation, decrease the facet spacing. So, but here, we can go to 23. You can ask the ChatGPT chat you're working with to recommend a small facet size to use for the evaluation of the DIC near a notch edge. So, okay. We can even try the smaller facet size after this. Okay, so let's see. This is a weird looking graphic, but this can sometimes happen. I found with these rigid body motion removed directional displacements. Remember, do not let a graphic scare you. The graphics can be very deceiving. You want to trust the and that was at step 0 anyway. You want to trust the probe values and look at the precisions. So yeah, we can see we've definitely refined the correlation. We're hugging the notch even more, and it's going to be harder to correlate at the notch tip because you're going to have speckle pattern breakdown here. There's going to be yielding, really necking here, material that's past ultimate strength at the tip. But let's see. So let's do so this has a precision of 0.2 millistrain. This has a precision of 0.3. So that's something you can work with. That's well into the elastic region. And so the idea is with the MATLAB code, most of this would be getting thrown out because it overlaps with the original correlation. but you'd have all this data in here would get added on to the previous correlation. And so let's see if we could go a little bit smaller of a facet size. Let's do this. Okay, and there we go. We got even closer. Look, we're almost right at the notch tip. Okay, and you could just go, when this finishes, you would probe and see what how these precisions look, if the precision is acceptable. Because we lowered the facet size, right? That's going to, in general, lower the precision. But it might not even have lowered it much at all. You have to see. Just depends. Now, let's say you were, for example, having trouble, you kept adjusting the facet size, like there, maybe we didn't get a correlation here. Maybe the load was higher and this speckle pattern here was degrading too much. So no matter how much you adjusted the setup here, the settings we just had here, you couldn't get a correlation here. So what could you do? Well, you could do a correlation that's fully dedicated to that region. So you want to leave room for a start point. A clear start point. You could probably pull this in. Okay, and run a correlation here. And so the general idea is the same idea in that smaller facet sizes are going to be useful so we can get up close here to the notch tip. But what's also coming into play, it wasn't an issue here, but for another test at a higher load, you could be having necking occurring here. So speckle pattern breakdown. So how do you deal with if the speckle pattern is breaking down a little bit? Well, in that case, rung steps could be helpful, strategically placing rung steps. But the issue there is that in that case, a larger facet size would be better because you just have the speckle patterns breaking down, but the larger the facet size, there's more, it can perhaps pick out certain features that still are distinctive from the reference step. So you have to find a good compromise between, test a few different settings and find the right compromise between the small facet size so you can get up close to the notch tip, but if the speckle pattern is breaking down, you can't make the facet size too small. So let's see. Let's just run this at 21. Okay, so let's see what we got. Residuum's getting a little bit higher. Not bad, though. No, not bad. Okay. So there we go. That's really useful. In this case, it looked like on the previous bigger correlation, we were able to get pretty close to the notch tip. But for other applications, maybe you weren't able to get that close with the full field analysis. And so this is really useful. You fill in a lot of gaps here near this notch tip. So let's see. And again, remember, don't let the graphics scare you. If you see a graphic and you might think to yourself, this data isn't correct, or you might be wondering, well, based on the settings that I chose to use, how do I know if the data is, the results I got are good results? You look at the precisions. You can trust that if you did the test right, according to the DanTech protocol, according to this video, and really in general, you could do the test wrong. If you do the test wrong, it's going to give you bad precisions. You'll get that. That's how you know if either it doesn't correlate at all, or you'll probe a value and it'll just be pure noise or close to pure noise. Then it's not good data. So we can probe these points. This is, if you look at the value, this has a precision of 0.3 millistrain. So that's solid. This one, 0.3 millistrain. So again, you'd use your MATLAB code to append any points that aren't currently in your main field onto your full text files, and then plot the full color scale results using MATLAB. Okay, and so now if we come back to our first test, and the question was, how can we potentially improve the correlation? Later in the test, when you started having this X region here just stopped correlating because you had so much necking and speckle pattern breakdown in these regions, how could you potentially fill in some of those gaps? Well, it's what we just talked about in terms of the notch tip and how to deal with speckle pattern breakdown. In general, it's going to be larger facet sizes. And here, since we're not dealing with like a crack tip or a notch edge, we can make the facet sizes large, and it's not an issue. We don't have to compromise here with trying to hug up next to an edge. So that's nice. We can make the facet sizes larger and then just put rung steps at different spots. Look for images where it seems like there's been a significant change, or maybe look for where it seems like the correlation starts to really fail. Go back to the correlation and look and see where the correlation is failing, and apply rung steps at different locations. Maybe try applying, you might try applying a lot of rung steps, 50 rung steps, 100 rung steps, and you'll lose a good bit of precision. And so instead of having a 0.3 millistrain precision, you might have maybe 1.1, 1.2, but that's still something you can work with to fill in gaps. Because whenever you append everything using MATLAB or Python to your main text file, you're going to include the precisions, right? It's not like you're going to leave out the precision. So you'll see the quality, any points you append, the quality of those points, the data at those points will be shown with the uncertainties. Okay, and so now let's take a look at one more example. So here is just a standard crack growth test. Okay, and so the main reason why I want to show this example is so, we can do a more official look at crack tip refinement, DIC correlation near a crack tip, and we can look at it from a slightly different angle than what we just looked at with that notch tip, because now here we have a propagating crack, right? And so let's see. Let's start a correlation here. We want to DIC training. And I don't know what the calibration file is, but what I'll do is I want to import the projection parameters from this evaluation here that was run, a year or so ago, 2 years ago, which I'm assuming the correct projection file or calibration file was used. So that's going to import the projection parameters. I'm going to set my own correlation parameters. We don't need the mask. I guess the coordinate system as well. Okay. So I'm going to leave every single step so the crack will grow to the end. I mean, maybe I'll take off, just to make this a little bit easier, some of these back end steps. No, we'll leave them all on. Why not? Okay. So, yeah, just to go through this whole process, this general process with you. So the first image looks like a good, clean image, so we'll leave that as the reference image. As far as rung steps, this is your first, you just collected these images. So now, right now, we're thinking about, we're going to do the full big picture correlation first. No, not a special correlation with we're not doing any refined correlation here, the full correlation. So we consider, do we need to delete any of the initial images because they can't be used as a reference image? No. So this first image is going to be the reference image. Now, do we want to take off perhaps some images off the back end that are just sort of taking a picture of the fractured plate? No, it looks like all of these images are showing the crack actively growing. Okay, so we don't need to remove any images at the end. Now, rung steps, yes. We probably want to just add a rung step since this is a constant rate of crack growth. I mean, we've got a lot of deformation occurring here, right? A lot of change in the image relative to the reference image. So for 2,400 total steps, let's add 5 rung steps, just evenly spaced. Again, because it's the rate of crack growth looks to be pretty even. So at around step 400, we'll make a rung step. 800. And then, yeah, that's it. Okay. For the mask definition, for the general full field test, you just want to go all the way up to each edge. And if the DIC can't correlate up to the edge, it won't. So now when we get to the crack, what we'll do is just hug the crack as well. And actually, we could bring these in a little bit closer. Again, if it doesn't correlate, it doesn't correlate. Okay, now, but what we also want to do here when it comes to the start points is, even though we've got one full region, we want to add 2 start points. And the reason why is because, so the idea is, in the beginning, we don't need 2 start points. But towards the end, we will, because we're going to have these 2 distinct regions. The system is going to go to a start point, and the idea is that that's where it starts. It's a good, clean correlation point that it can branch off from to the surrounding regions. Well, once you have a crack that's separating these 2 areas, these 2 distinct regions, what will most likely happen is it won't correlate past the crack after some point. The crack creates these 2 different regions, and it branches off from here or here, and it doesn't correlate past the crack. And so this gets uncorrelated. So here we need 2 start points. Now the evaluation settings will do the high end of the facet size range for this general full field correlation. So I'll actually make this, and then let's do that. And so, yeah, you can see now there's two start points. We created two start points. So here, when running the start point search, there needs to be two start points. And each is going to have its own residuum. And that's acceptable. Now, while this runs, if we come back to the evaluation settings, I don't want to change anything or else it'll halt the correlation. So you've got these maximum permissible values here, right? And so we talked about how when it comes to the start point search, it will fail. A certain image won't go through the correlation process. It'll be rejected if the 3D residuum for that step is 0.4 or higher. And so what you can do is another strategy is if you're, for the test we just looked at with the necking in that X region, for the center circular notch test we were just looking at with the regions of necking failing late in failing the correlation late in the test, what you could also consider is bumping up these thresholds a little bit. Bump this up to 0.2, 0.3. Bump up the residuum if the lighting conditions aren't optimum. And again, so like you might be thinking, well, I don't want to bump this up too much and get correlated results that are incorrect. Well, no, you'll see that they're incorrect. You'll look at probe the values and you'll see that you're looking at just pure noise or close to pure noise. And so it will tell you. But yes, in general, if you bump these values up and the correlation then succeeds when previously it was failing, well, what's going to happen is the values you get are going to, in general, have higher precisions. But when you append this data onto your existing field of data, those precisions will be reported with the values. So you'll see the quality of the data. The residuums are starting to climb a little bit. Hope they don't continue to climb too much as we get to later steps. Okay, so the residuum held up all the way to the end. Okay, so let's see what we've got. Okay. Not bad for the general full field, the first general big picture full field correlation. Okay, so this is actually pretty good as far as how close we got to the crack tip, but we could get a little bit closer and perhaps even a little bit closer to these edges. So let's reset. And we'll start with the crack tip refinement. And so I'll just go ahead and leave the rung steps. You could potentially consider sort of starting the analysis from scratch here and reasoning through if you want to add rung steps, but I'll just go ahead and leave them. And I'm saying that because the speckle pattern, again, the speckle pattern near a crack tip is going to be inevitably breaking down a little bit. So rung steps are going to be helpful to some extent. But I guess I just mentioned potentially removing them because the original reason the rung steps were added was because the specimen as a whole was changing so much. But here we're going to be zoomed in on the crack tip. So we're going to be ignoring the bulk of the specimen. So let's see. We'll do, so we want to leave some room for start points, or a start point in this case. Okay, there we go. Now we want smaller facet sizes here. So let's do this. Well, since the masked region is so small, I can make this a little bit smaller. And let's nudge this up a little bit and see what happens. Just curious. And I'll leave the residuum. Okay. So now we only have a single start point here. So these start points are wrong. So let's delete. And now let's see if it resets. It should reset. There we go. Okay, so that's the right start point. And okay. Let's see what we get. Now when it comes to hugging these edges here, I mean, you might want to add even more rung steps, right? Maybe you need a lot of rung steps. And yes, that would be at the potential expense of precision, but if it goes from a precision of 0.3, 0.5 millistrain to 0.9, 1.0, that's not so bad, especially when you're just trying to fill in some of your correlation gaps of the big picture correlation. And maybe I wasn't thinking about this right. I'm trying to think if maybe more rung steps, well, we left the rung steps here anyway, but maybe more rung steps than I'm thinking are even needed for this crack tip analysis, because the crack tip it's propagating through the entire specimen. So yeah, maybe a correlation like a crack growth analysis correlation might really work well with a lot of rung steps. You can just try it out and see the resulting precisions of the values you get. Now, the start point might be problematic. Yeah, so the start point doesn't move in space with the specimen, so this could be an issue. But this is all great for this instructional video to give you a sense for how this works. So yeah, I'm assuming this is going to start failing once there's no start point available. Or no, it's moving. Okay, it's tracking with the specimen. I thought maybe it was fixed in space, so we might be okay. And so I bet adding a rung step at a strategic location right when this starts to open up would be very helpful. Past this point, yes, the image is changing, but there's a level of consistency, a level of symmetry as the crack propagates. But going from the very small crack to like this point, I would imagine that a group of rung steps would be helpful for the correlation. We're not going to do the correlation in this video, but for the refined correlation, potentially trying to get closer to this edge, and even maybe for this correlation as well near the notch. Again, just run test correlations and see the quality of the resulting data you get in terms of the precisions. .060, very good, residuum. .044. Okay, so let's see how this came out. No, so that did not work. So let's try and make this region bigger. So let's see. Let's try this. Let's try this, and we'll put 2 start points. Let's see how this works. Evaluation settings, we'll leave. Well, let me nudge this up a little bit. And I'm doing that because the correlation came out pretty well with the original facet size. So let's do this. Okay, and we want to reset the mask. Let's try this. Okay, so it looks like so I'm wondering if this is an issue, the fact that the start points, shouldn't they be sort of following the crack? I'm not sure. So let's run the correlation. All right, there we go. There we go. Okay. But we didn't get much closer to the crack. And so again, some strategically placed rung steps, I bet would be helpful if you want to try and really get a little bit closer here. Or you could bump up those threshold values a little bit more. Let's see what we got. And again, the idea is if you really wanted to, well, there we go. Now we're right at the crack tip. Like if you really wanted to just get some value, some non-useless value, well, then you could just really increase the facet size or push up the thresholds, push the limits of what of what's going to allow you to get a correlation, and then just check the data and see if it's either if it's not pure noise or close to pure noise, but maybe it's not the most precise. It's still you can report that value. Same idea here. If you're trying to, I mean, this is pretty close to these edges. and with this being a difficult, it's pretty difficult to correlate. This isn't a static notch, right? These edges came out of nowhere. They weren't even present in the reference image, but that's what you could use. A more strategic placement of the rung steps, I bet, would help here. Rung steps right around, even a 3 or 4 rung steps right around these time points here, of right when this starts opening up. And maybe even since the images are changing so significantly from one image to the next, you just need a rung step every 50 images, every 20 images. Again, that might seem like a lot in terms of you're going to lose precision, but you still might get values that aren't pure noise, that you could at least append to your data, to the full field data you have. So why is it seems to be getting worse as the crack gets longer, but then for the main correlation, the global correlation, that's not an issue at all. It must have something to do with the start points. It must be a lot more favorable for even the local crack tip analysis, even the localized regions, to have start points just out here in the general field. I wonder if, but this is hugging the edge pretty well. I wonder if this is quality data. Hmm. Yeah. So my guess is that having the start points sort of out here allow the at each step the algorithm can start in sort of a clean area that's away from. Yeah, so like one of the rules when it comes to start points is it needs to be in a stable region. And so what I'm doing here is, yes, initially the region looks stable where I select the start points at step 1, but at later steps it's not stable. So, right, these start point locations here ultimately are not stable as are points out here. So let's try this. Let's try. And now let's give it some room here for some, we even want to go far enough out because the crack's going to come out here for some nice stable start points. Let's try this and see what happens here. Okay, so we'll do like that and like that. Let's see what this does. We'll use the same. In fact, I'll go back since we're trying to get close to the crack tip. and it looks like it's the start points that was causing this issue. I'll go back to the smaller facet size. And okay, now let's see. We need to delete these old start points. There we go. Let's see how this does. Okay, so this is, at least for this step, this looks a lot better. Hopefully this is holding up for other steps. Okay, so it looks like the start points can get tricky when you've got such a dynamically changing specimen like this. But I'm glad that that happened, because I feel like that gave you a good illustration of how start points work, and how to correlate a crack growth test like this. So just a reminder, all we've done here, we had the original large field with the large facet sizes, and we couldn't make, in general, we would make, when we're doing a refined analysis, a specialized analysis of a crack tip or a notch, we would have a much smaller mask. But this is a special case where we still need a relatively big mask, but we still went ahead and lowered the facet size and bumped up the thresholds, the acceptable thresholds. So let's see. So sometimes it's not, so that's right up at the notch tip. Let's see if we can put a probe here. So 695 plus or minus 4 millistrain. That's well past the elastic region, but the signal to noise ratio is good. And this makes sense. I mean, this is, material separation. Okay, and so there we go. That should give you a good foundation for how to run correlations on DIC image sets and get reliable data, as well as refining the correlations with respect to special cases like near notches and crack tips, and then combining all of that data together to get net final full field results.